If we have function z, which is a function on two variables fx, x and y, say x0, y0 is a critical point of this function if firstly we have a point x0, y0, and we can draw disk around that point, and function would be defined on the disk. Is defined on the whole disk around point x0, y0, and first either derivative with respect to x at a given point equals to 0, and derivative with respect to y at x0, y0 equals to 0, or partial derivative with respect to x at x0, y0 does not exist, or partial derivative with respect to y at x0, y0 does not exist. What's the definition of critical point? Definition of a critical point. Example, here we have function z which equals to 4 minus x squared minus y squared, and we want to find critical points. We need to find partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to x is negative to x, partial derivative with respect to y is negative to y. Both partial derivatives are defined for all x and y's, so we want to see where y equals to 0. So partial derivative with respect to x equals to 0, negative to x equals to 0, so from here we get x equals to 0. Partial derivative with respect to y equals to 0, negative to y equals to 0, so from here we get y equals to 0. So we conclude we have only one point to consider, so 0 is 0, so we have only the critical point here. Zero and 0. Second example, we consider function z which equals to x squared plus y squared plus 2x, and we want to find its critical points. Find partial derivative with respect to x, 2x plus 2, partial derivative with respect to y, 2y, partial derivative with respect to x equals to 0, means 2x plus 2 equals to 0, means x equals to negative 1. Partial derivative with respect to y equals to 0, means 2y equals to 0, means y equals to 0, so we conclude that our critical point is negative 1 and 0. So critical point for this problem, negative 1, 0. Definition. Let z be function on x and y. And let x0, y0 p points so that function is defined on a disk around that given point. So f is defined on open disk around x0, y0. We say that function f has local max at point x0, y0 if f of x0, y0 is greater or equal than f of xy for all points xy on that disk. Local max, we say f has global max at point x0, y0 if f of x0, y0 is greater or equal than f of xy for all points from the domain of function f. Similarly, we define local mean and global mean. Two theorems about function of two variables. We have function z, which is function of two variables. And again, we assume that it's defined on a disk around point x0, y0. Function f of xy is defined on disk around 0, y0 if x0, y0 is an extremer of f of xy, and if partial derivatives with respect to x and with respect to y at x0, y0 exist. So if two partial derivatives with respect to x and with respect to y exist at a given point, then point with coordinates x0, y0 is a critical point. That's the first theorem. So it tells us how to find critical point, how to find extrema. So candidates for extrema are going to be critical points. And second theorem will tell us how to classify critical points. Theorem, second derivative test. So we have x0, y0, we have disk around it, and we assume that function f of xy are first and second order derivatives defined on the disk. Let's assume that we have partial derivative with respect to x at x0, y0 equals to 0, and partial derivative with respect to y at x0, y0 equals to 0. So we have critical point at x0, y0. Then we define, when we calculate quantity d, which equals to second derivative with respect to x at a given point x0, y0 multiplied by second derivative with respect to y twice at x0, y0. We subtract partial derivative with respect to xy at a given point squared. Now we have three possibilities. Now we have three possibilities for d. First one, d is bigger than 0. Then at a given point x0, y0, function has extremum. Particularly if second derivative with respect to x at a point bigger than 0, then it is local mean. If second derivative with respect to x at x0, y0 is less than 0, then x0, y0 is local max. Second possibility, d is less than 0, then at x0, y0, function f of x, y has neither max nor min. So x0, y0 is so-called saddle point. And the third possibility, if d equals to 0, the test is inconclusive. So second derivative test tells us by calculating d whenever we have extremum at a point or we don't. If d is bigger than 0, we have extremum, d less than 0, we have a saddle point, d equals to 0, test inconclusive. And also, when d bigger than 0, by looking at the sign over second derivative, we can conclude whenever we have local max or local min. Next example, we have a function of x and y which equals 10 plus 12 x minus 12 y minus 3x squared minus 2y squared. We want to find critical points and classify them. Partial derivative with respect to x equals to 12 minus 6x. Partial derivative with respect to y equals negative 12 minus 4y. We set partial derivative with respect to x and partial derivative with respect to y equals to 0, so we get 12 minus 6x equals to 0, negative 12 minus 4y equals to 0. From the first one we're going to get x equals to 2, 12 minus 6x equals to 0, x equals to 2. From the second one we're going to get y equals to negative 3. So we have critical point 2 and negative 3. Now we want to use the second derivative test to classify the point. So we want to calculate d at point 2 minus 3. To calculate d, we need to find second derivative. So second derivative with respect to x is going to be minus 6. Second derivative with respect to y is going to be minus 4. Derivative with respect to x, y is going to be 0. So d is going to be negative 6. Second derivative with respect to x times negative 4. Second derivative with respect to y minus 0 squared. So it equals to 24. So d is bigger than 0. We conclude that we have extrema. Now, because second derivative with respect to x equals to negative 6 less than 0, we conclude that at 2 minus 3, function f of x, y has local max. One more example. If we have function of xy which equals to x squared plus 4xy plus 2y squared plus 4x minus 8y plus 13, and we want to find critical points and classify them. Find and classify critical points. Derivative with respect to x, derivative of x squared is 2x, derivative of 4xy is 4y, derivative of 4x is 4, rest is constant with respect to x. So we're going to x, sorry. Derivative with respect to y, derivative of 4xy is 4x, derivative of 2y squared is 4y, minus 8. We set both derivatives equal to 0, so we have 2x plus 4y plus 4 equals to 0, and we have 4x plus 4y minus 8 equals to 0. Now we have to solve that system of linear equations. So for example, we can subtract them. So we subtract, we're going 2x minus 4x is negative 2x. 4y minus 4y is 0, 4 minus 8, 4 minus minus 8 plus 12 equals to 0. From here we conclude that substituting x equals to 0 back in any of these equations, for example into the first one, we're going to get 2 times 6 plus 4y plus 4 equals to 0, 12 plus 6, 12 plus 4 is 16, so 4y equals to negative 16, so y equals to negative 6. So we have critical point, x equals to 6, y equals to negative 4. Now we calculate d at this point. We want to apply second derivative test. So we want to calculate d. To calculate d, we need to find second derivative with respect to x. It's going to be 2. Second derivative with respect to y is going to be 4. And derivative with respect to xy will be 4. So now we are ready to calculate d. So 2 times 4 minus 4 squared is going to be equal to negative 8. 8 minus 16 is negative 8. So d is less than 0, so we conclude it's not extremer. So it's saddle point. So at critical point 6 and negative 4, function f of x, y has saddle